Which person? Okay.
I think we're live. Can you check the stream to make sure you see it on your
Yep.
end?
I'll check. Yep.
Is it good?
No, it still hasn't loaded yet. Uh, give it 30 more seconds. Nope. Still.
Yeah.
Okay. Yeah. We are live.
All right. Hello and welcome to the Corecast. I am your host, Tim.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to it. Also, future announcement, we are in the midst of planning to put out shorts for people who, may not be able to catch the full episode. So if there's any topic you'd love to see us cover in like a sub 1 minute long format, please do let us know and we're open to suggestions. So yeah, so without further ado, let's get to it. So Tim, I thought this was a really interesting thing where we're talking about bringing a math specific thing into physics. And so just to give the listeners some context, and feel free to add anything if I miss anything. We're going to talk about I would say the Millennium Prize problem that's most tied to physics. Millennium Prize problems, for people that don't know, are these $1 million mathematical problems that are very difficult to solve. Things you might have heard of, like P versus NP from computer science, Riemann hypothesis behind prime numbers, and a few others. The one that was solved was called the Poincaré conjecture. There's a whole interesting history behind that. And so this one, Tim, I thought would be interesting to discuss. So I guess why don't we start off before we describe exactly what the problem is and all the lingo behind it? Maybe you can like give a very brief overview of like what it is, and then kind of really set up the motivation of like why are we even considering for this problem? Like why is it even
Mm.
worth talking about? Like what's the big deal about this?
Yeah, sure. So let's go back to the Millennium Prize problem a little bit. And I think we can argue that there are two of the Millennium Prize problem that are physics related. The first one, probably maybe more people are familiar with, but I could be wrong. Is the Navier-Stokes equation, or proving that there is a solution or there isn't a solution. But that has to do with fluid dynamics, and one can argue that the equation may or may not be exact, but it is somewhat physics related, sure. The second one is called, and this is the title of today's discussion, is called the Yang-Mills and the mass gap problem. And that actually, in my opinion, has more to do with physics. And that problem is born from a desire to understand a particular fundamental physics theory called the Yang-Mills theory. And why is that a big deal? As we will find out, Yang-Mills theory is basically a simplified version of the strong forces when you strip away all the unnecessary fluff. And why mass gap? It turns out that most of the mass that we see in our universe, protons and neutrons and all that, that mass does not come from the Higgs boson. It comes from the strong force itself. So it's a mass born of a essentially force itself. So force is able to generate mass. And solving this Millennium Prize problem would mean understanding mathematically where that comes from. And so that's why I think it has a unique physical significance.
Gotcha. So I just want to like ask one question about that before we
Mhm.
proceed forward. So what you're saying is that if we look at the mass of a proton, it's not due to the Higgs boson, as most of the lore on Higgs bosons, like, oh, it gives mass to particles. It's actually really coming from the strong force itself.
Right, yeah. So if you kind of just do a little bit of Wikipedia search, you may find you can do some, I don't know, pen and paper simple calculations. The first thing you'll find that a proton is made up of up and down quarks, right? So you can, and normally in textbook you say a proton is made up of two up quarks and one down quark, although that's wrong because we know that protons also can contain antiquarks and whatnot. But in any case, you can try to add up the mass of all these quarks. Quarks are actually very,
Mhm.
very light. And if you add them up, you will not get the mass of the proton. You will be way short. You come up short. So while and the mass of the quarks comes from the Higgs field. I think we probably talked about that a few episodes back, so I won't reiterate some of the points there. But that only contributes to a small fraction of the masses that we see. So like my hand, my body, tables, most of the mass comes from the mass of the protons and the neutrons. The electrons are somewhat negligible. So the majority of them comes from the mass of protons and neutrons. And the mass of protons and neutrons comes from the force itself, because if you add up the mass of the quarks, they do not add up.
Got it, got it. Yeah, no, that's a nice segue into our discussion. So let's start off and say like, what the heck is Yang-Mills theory? Like that, I mean, I'm assuming it's two guys, one named Yang, one named Mills, but like, yeah, just what is this and what's the significance of Yang-Mills
Yeah,
in particle physics?
let's just give a little bit of historical context. I think the Yang-Mills
Mm,
theory were developed in the 1950s, 53 to be precise, and it's by two physicists. I'm going to try not butcher the name there. The Yang portion, it's a Chinese name, is Yang Zhenming. That's the physicist, and then Robert Mills, and they developed the theory at the Brookhaven National Laboratory. Um, so the reason for the development was back in the days, we only have a theory for electromagnetism, basically the theory of light, right? And the theory of how electrons orbit the proton, how atoms roughly form. But really don't understand how the nucleus bind together or how radioactive decay happens. And people realize that, you know, if if we just have more copies of electromagnetism, that's not enough. Like that does not explain the strong force or the electroweak forces. So there was an effort trying to bridge that gap. Like how can we generalize electromagnetism in a way that gives us forces like the strong force that's responsible for holding nucleus together, and also for radioactive decay, the weak force. And it turns out that that theory, as was known later, is the Yang-Mills theory.
got it, got it. I guess so. I guess how does like maybe we can qualitatively describe how does the strong force differ from electromagnetism? Like, can't you just say it's like, I mean, the strong force carriers are particles called gluons. Can't you say those are like just photons? There's like eight of them or something like that. Can't you just come up with a theory with eight photons, eight different kinds of photons, and you're done? Like, what do we need
Mhm.
more?
Yeah, so the difference is, at the base level, and of course, now we know that there are eight different gluons, and you can retrospectively think back, hey, what if we just have eight copies of electromagnetism? What goes wrong, right?
Hmm.
The
Hmm.
problem is we now know that these particles themselves, they self-interact. And that does not happen to light. Like light does not interact with life itself. Um, but we know that the strong forces interact with itself. That's why the strong forces get so strong, because like there's a compounding effect. Like one gluon sees another gluon, they may be attractive or repulsive, but it's I think it's more attractive versus repulsive, but you know don't know the precise numbers.
Hmm.
But that fact alone means that electromagnetism is not enough. You need a little extra. You need some extra interactions between the forces themselves. So basically, you need something that accounts for the fact that the forces also generate forces.
I see. So, okay, so I just want to understand this. Like, if we were to take, let's say, for the strong force, eight copies of like photons, maybe eight different kinds of photons, and you try to just do eight different copies of electromagnetism. Are you saying that like these photons would just pass through each other, wouldn't really like interact with each other in electromagnetism, or how do I think about that?
Yeah, exactly. They will just pass right through one another.
Hmm. And and so yeah, so you're mentioning like, there's this self interaction, and that self interaction is this sort of feedback loop that allows the force to have like a very strong attraction to itself, which confines, like, that's why the proton is not like all over the place, and the neutrons all over the place, but very like localized. Is that the effect of having the self interaction?
Yes, 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 yeah. So the self interaction is key. Yeah.
Mhm. I see. um so it's interesting that you say that a force like generates, like a force itself also interacts. I mean, how, I guess, how do we like know this, and how does this relate back to Yang Mills?
Yeah, yeah. It's a good question, and some of that is experimental evidence, right? I mean,
Hmm.
it turns out that it turns out that if you hit protons against each other at very very high energy,
Hmm.
what gets collided is actually, well, it's a constituent of the protons, right? But it turns out that most of that constituent is actually the forces themselves, the gluons, right? And when we collide
Hmm.
protons together, these gluons, we see what comes out. And actually, they come out copiously. Like gluons and gluons collide, they produce a lot of stuff. And you can do the same thing with two laser beam. If you shoot one laser beam over another, you might produce some stuff, but the amount of stuff that you produce is way less. So there's experimental evidence to suggest that, look, the force carriers themselves are very interacting. The issue there? I think you got muted. Yeah.
Oh, sorry, you were frozen for a bit.
Oh, okay.
Sorry about that. Yeah, yeah. So okay, so then one question I have regarding that is that, let me think, what was I going to say? So you have these gluons that can interact amongst themselves. And if you shoot gluon, you collide two protons together, you get a lot more stuff than if you were to shoot two laser beams at each other. And that's how you can tell there's this self interaction piece.
Mhm.
Now, I want to come back to Yang Mills. So, from my understanding of what you've mentioned so far, Yang Mills is a way to essentially generalize electromagnetism to the strong force with, eight self-interacting gluons, these force carriers. I'm pretty sure, Yang Mills isn't the only way you could generalize. So why Yang Mills? Like, what if I were to just like not know anything about Yang Mills, and I just say, let me just introduce these like interaction terms that have this thing determined experimentally. Like I do experiments, and then I, have some model, and it has models interactions, has some coefficients that represent the strength of the interaction. Yeah. Why not start with that approach?
Yeah, yeah, and in some sense, you could go through that thought experiment. And initially, when historically when they first started developing this idea, yeah, I'm sure they try all kinds of ad hoc way to do it. Like for example, one thing you can do is, let's say you take two copies of electromagnetism and say that, hey, they attract each other. Why not? Let's do that, right?
Hmm.
It turns out that if you do that, you develop pathologies for your theory. You find out that, hey, they might become too attractive, and then the numbers will become nonsense because quantum physics is probabilistic. You might find out
Hmm.
that, hey, at certain energies they become so attractive that the probability of them doing something becomes like 110%. Like that doesn't make sense. Probability has to be less
Hmm.
than one, less than or equal to 100%, right? So if you play this game, you just add interactions one term after the next, you realize that your interaction has to follow a particular pattern, right? Um,
Hmm.
and it turns out that if you organize those patterns together, they have a particular kinds of symmetry. And we talked about symmetry in the past. If you have symmetry, it turns out your theory, the pathology of those theories go away, right? Um, so
Hmm.
The Yang Mills theory, why it isn't just something trivial, is that
Mm.
they were able to generalize from a symmetry perspective to say that, hey, look, you when you have forces that self interact, they can't just self interact in some arbitrary way. You can't just be like, hey, well, these two guys are attracted, these two guys are repulsive. No, you can't do that. It's mathematically inconsistent. The only way to consistently do it is to have some sort of symmetry principle guiding behind them, and then your theory all of a sudden becomes almost like beautiful. It works. It becomes beautiful again, right?
So what you're saying is like if I went through this whole process of adding in these terms and I do some computation with my theory and it gives me nonsensical results, I'm like, okay, I'm just gonna add in more and more, even more terms to counteract those things, and it just keeps going. Eventually, I'll end up with the Yang-Mills.
Yeah, exactly. And it turns out that, as people find out later, that the same thing works for Einstein's theory. I know
Mm.
that people think that Einstein's theory is about, there's always this cartoon picture of like the curvature of space and time causes gravity to move in a particular way. You can also take this brute force approach. Imagine you didn't know Einstein's theory. You just say, hey, graviton can also create gravity, because that's what Einstein's theory says. Gravity itself can generate gravity, right? Let's say you just say that. Let's do it. And then you see that, well, the theory is a little bit inconsistent. And then it turns out that you have to organize your interaction in that way. And by the end of the day, if you do it well, you realize that all your terms organize in a beautiful set of equations that are highly symmetrical, that represent a sort of geometry. And historically, I think when Einstein first developed his theory, he had pages and pages of equations, almost like really hard to understand. And when people realized the geometry behind it, they were able to simplify it to one line, basically. Like, it's a beautiful Einstein's equation.
Mm.
You can look up in Wikipedia, it's one line. But Yang-Mills theory is somewhat similar if you take this brute force approach. You can say, hey, forces themselves can be attractive or repulsive. You add these interactions, and you keep playing this game until you add enough terms that the theory become consistent. And then you realize, aha, guess what? I actually have a geometry behind it. Yang-Mills theory is actually describing an abstract space, similar to Einstein in some ways. It's describing a sort of abstract space that are curving up and down, left and right. The curvature of these, abstract dimensions are the electro and magnetic fields that we experience. So Yang-Mills were able to generalize that. So they developed the equivalents of electric and magnetic field for the strong force, for example, or for the radioactive decay, the weak force. So you can have the
Mm.
strong electric field, the strong magnetic field, or the weak magnetic field, weak electric fields.
Got it, got it. That's really interesting. There's parallels with gravity, although I'm not sure exactly if it's one to one. I mean, maybe we can talk about later how
Mm.
where the analogy breaks down. So look, I want to turn our discussion over to mass gap because we so far have set the stage of what Yang
Mm.
Mills is, and so now to discuss this Millennium Prize problem that is Yang Mills and the mass gap. So I'm just going to ask you point blank, what is a mass gap? And just like, yeah, what is the significance of it?
Yeah, the mass gap actually is a very it's an observation, right? Like, we look at the real world around us. Things have masses. You don't see
Hmm.
things without mass. Well, there are certain particles without mass, but most of the matter has mass, right?
Hmm.
Um, so, but why is it not just mass, but mass gap, right? It just to avoid some sort of pathological scenarios. Like, you could have a theory that has mass, that has, let's say, infinite number of particles. Some of them have mass 1, some of them has mass zero point 0.1, and then 0.01, 0.001, right? You can have an infinite ladder that keeps going down to zero. We want to avoid that pathological situation, because we know that in the real world, when we have a theory that's kind of like the Yang-Mills theory, things just have mass. There just is a lower bound of masses, and they're all around the similar masses. Like, if you look at the proton and neutron, they have similar masses. Even if you look at things like pions, or like particles that are linked to the strong forces, they have, give or take, masses that are maybe a factor of 10, 100 within some window. They don't have these pathological behavior. So in the real world, there is a mass gap. The question is, in the hypothetical world of Yang-Mills theory in general, is there also a mass gap?
I see. So what you're saying is the mass gap just is referring to that in our universe there, matter has mass. It's non-zero. Otherwise, if people stepped on the scale, they would just say that we all weigh 0 pounds. And so it's that would you say it's like the difference in expectation that I guess in a theory you would expect there to be zero mass and then there's mass, or a gap usually means to me that there's some discrepancy of, and you're starting at zero. So why
Mm.
significance of like zero mass? And does gap mean it differs from our expectation, or yeah, what is going on with that?
Yeah, I think there is a little bit of expectation. Like from an experimental perspective, it seems such a
Mm,
trivial thing, right? Like all the things we see in the world has a mass gap. It's just that it's either zero or if your mass is not zero, it's something above zero. You don't get this pathological behavior, right? But
yep.
let's think about the from the perspective of Millennium Prize problem, right? At the end of the day, it is a mathematical problem, right? They're not trying to solve physics. Physics has experiments, but math just has logic, right? But
Mm,
first, let me clarify this. Our world doesn't just have Yang-Mills theory. Our world is Yang-Mills theory plus some other stuff, plus matter in particular, right? We have quarks and electrons and neutrinos and all that, and the Higgs field, the Higgs boson, right? The mathematical counterpart is a simplified version of that. It's what if you imagine a theory like our universe, but you delete all the matter. You just have pure forces and also no gravity,
mm,
right? What if you have a theory of pure force with no matter
mm,
whatsoever? Pure force.
mm,
Is there still a mass? And we have some experimental as in simulation evidence, some tangential hint in math that suggests that we do indeed. So a mass could arise from pure force. And this is where that discrepancy comes from, because when you first write down a theory of pure force, like imagine you're playing a game, you enter a theory of pure force, and it will spit out the physics of the pure force, right? What is the input of this
mm,
game? The game is just some number, like how strong is your pure force? Is your pure force strength of 1? Does it have a strength of zero point 0.1 or 0.01, right? And then somehow inside the computer, that number is going to convert into a mass, which is very, very, very strange. So I think the word mass gap capture this strangeness because you do not expect you're not expecting a mass to come out. But then we know that from computer simulations and some other mathematical hints that nevertheless, a mass emerges. So what gives? So this is sort of the
mm.
conundrum, the source of this Millennium Prize problem.
So to summarize what you're saying is that in this theory you only have force. There's no matter. So the matter, as mass, but you're throwing it out. You're simplifying the theory down to only forces. And forces don't have necessarily a mass associated with it. When I think of electromagnetism,
Mm.
I don't really think of like something in kilograms, or in the case of a strong force, I'm just thinking about the force carrier particles. And yet, um, when we were talking about the beginning of the episode, we were talking about that most of the mass of a proton, neutron, and basically all of matter that we can see uh, comes from the strong force itself, not from the individual quarks. And so Yang Mills, this theory should produce, theoretically speaking, the majority of this mass, where it comes from. And it's not exactly clear where that's coming from, because you've not entered in any like mass units into your theory. It's just force and strength of force, and all those sorts of things. Is that in a nutshell what you're trying to say?
Yeah, exactly. And I just want to reiterate how strange that is. Like, imagine you have a program that converts something to mass, right? Like, imagine you have
Mm,
a formula, right? And your
mm,
input is like zero point 0.1, zero point zero 0.01. Like, how do you convert that to a kilogram? Like, the theory doesn't know about kilogram. It doesn't know about the atomic units. It knows nothing about pounds, kilograms, and grams. Like, how does it know to create a mass? So that's why it's such a conundrum. And this problem, at least in physics, we have some. Keep in mind that physics is not mathematically rigorous. In physics, we have an explanation. This is called dimensional transmutation. And
mm.
I mean, this is just a word salad on what it does. Basically, it just says that a mass is created out of thin air, kind of like do something as if something is magical, right? Uh, but the crux of the Millennium Prize problem is that where is the mathematical rigor to prove that it does work that way, right? So that's kind of
Hmm.
the missing gap of the understanding.
So I guess one question I have is if you didn't let's say you couldn't observe reality. You were just trapped in a room and you were given this Yang-Mills theory. And with your current knowledge as it is right now, the current knowledge of particle physics from a theoretical standpoint, what you would say is that the output of this theory, you wouldn't be able to tell if there is mass. You would just output what the behavior of the force is, but it would be unclear whether even mass exists.
Yeah, exactly.
Mm,
But physics kind of gives you some hint what the solution
mm,
is, right? And I think this Millennium Prize problem is unique because Yang-Mills theory by itself is not well defined. Like Yang-Mills theory ultimately is a subset of quantum field theory, which is the theoretical
mm,
framework that we do particle physics calculations on. And this theoretical framework is not well defined. It doesn't have a solid mathematical foundation, meaning that there isn't a set of axioms that are logically consistent that we know, right? Um,
mm,
so in physics, we know that the theory is incomplete. So what may be happening is that if you try to write down Yang-Mills theory, um, there actually may be a parameter, a mass parameter secretly hidden in the theory that you just don't know that it was there. Like it means that
mm.
you actually could not define your theory unless you have something like a mass parameter that you use to define it. So that might be one of the hint. But the Millennium Prize problem is to formalize it. How do you even formalize that theory? Like what framework is needed for you to do that?
I see, I see. Um, I guess so. Okay, so then clearly, the scenario laid out is not the world we live in. We can do experiments. We see that protons have mass, neutrons have mass, and this theory can't predict mass as explicitly. How does physics reconcile this? Why is this even accepted if it can't produce mass? Like, yeah, why? Yeah.
Yeah, the thing is, in physics, I mean, in some sense, physics is even more complicated, right? Because not only do we have Yang-Mills theory, we have extra matter on top of it. We also have the Higgs field, which complicate things a whole lot. But look, the lucky thing is in physics we have experiments. Even though physics cannot exactly predict the proton mass, we just we can measure it, and that's good enough. So, so for a lot of physicists, we just kind of like, well, let's just move on because the problem is too hard. Like, why bother? Why bother toiling yourself trying to prove something when you can just measure it, right? So,
That's a fair point. One question I have about this is what if you were to add in quarks? Even the quarks have like very small amounts of mass, and I know if you add them up, won't add up to the mass of the proton. But what if you require like matter in your theory in order to output mass, even if the contribution of the initial masses is very small?
um, we'll probably discuss this later. so pure Yang-Mills theory, there is no matter. You could try to add matter to modify the theory a little
Mm.
bit, and it does get
Yeah.
modified. Actually, indeed, it does.
Hmm.
And sometimes you can add enough matter that the theory becomes solved. Actually,
Hmm.
we'll probably save it for the next episode. You could try to make supersymmetry work for you. Remember that supersymmetry is a
Hmm.
tool for hypothetical worlds that make your math more tractable. So adding matter does change the theory. It could make it
Hmm.
more tractable or more intractable. Uh,
Mm.
Probably for our world, it makes it a little more intractable. But basically, because now the interaction between matter and force has to be combined, and it gets even more complicated. So I don't know if we
Mm.
want to go into that. The Yang Mill, in some ways, is a stripped down version of this. Yeah.
Mm. That's fair. I mean, we can save it for a later episode. I was just very curious. Uh, yeah. So one of my last questions is, to solve this problem, does it require any new? I mean, this is actually a very interesting problem because it's a Fields Medal worthy problem, but it's also a physics problem. So I guess the essence of my question is this a math problem, a physics problem? Would you require additional experimental evidence if you come up with some new mechanism to explain where the mass comes from, but need to verify that that works experimentally so you don't break the theory and its predictions?
I mean, that's a great question because, I mean, it is strange because like most of the Millennium problems are pretty well defined mathematically. Like there's a mathematical
Mm.
framework to talk about it. But this
Hmm.
one, on the other hand, does not. Even though it says something about Yang-Mills theory, but Yang-Mills theory has not it's not well defined fully mathematically.
Hmm.
So I would say that it really is a mathematical problem, and I think
Mm.
it's um, and the crux of the problem really is trying to define it because we don't know how. And I think the crux of the mass gap is to find out why the theory needs a mass parameter to be defined properly.
Mm.
And when that happens, how that translates to the way the theory behaves. So, I mean, I think physics can probably play a role to help us understand how to tackle this problem, where this comes from. Like, for example, as I was alluded to earlier, you could modify the theory a little bit, twist it a little bit, mold it a little bit to make it solvable in some ways, and then you can see its
Mm.
behavior, mathematically. Um, so I think these extra mathematical data perhaps can help us ultimately solve the mass gap problem. But yeah, I think at the end of the day, it is a math problem. You know, if someone were to solve it, it will definitely be a great triumph for math and physics. But I'm not sure it will be Nobel Prize worthy. Probably, maybe not,
Mm.
or maybe hard to say. Hard to say.
Any speculations on I guess if this can be resolved or if yeah, just curious your thoughts, speculative thoughts on this.
I mean, that's really tough.
And speculative.
I think ultimately there may ultimately be a mathematical framework to talk about the Yang-Mills theory.
Uh-huh.
I I mean I think nature is logical and probably that framework exists. It might be drastically different from how we formulate the theory right here
Mm.
because um, the conventional wisdom is that Yang-Mills theory is, as I was saying, it's sort of like Einstein's theory. It's describing curvature of some geometric object. Um,
Mm.
but there may be different viewpoints. Maybe you can disassemble these curvature into different objects and view it differently. And in my mind, that's if we were going to solve it one day, probably it will have to be a different way of looking at it, and then we'll realize that all of a sudden the theory is not well defined until you input in this extra parameter, the mass gap in some sense. And
Mhm.
then maybe someone can collect that $1 million. But very interesting to see.
Actually, I didn't want to go down this speculative route. I was going to ask you, what would be your prediction of how much $1 million would be worth by the time this problem is solved?
I guess they don't increase the prize pool, right? But
Yeah.
but probably
Uh,
the $1 million is a small prize compared to the achievement and the satisfaction one will get for really understanding the Yang Mills problem. So
yeah. So we have an audience question that just came in. Was there any similarity between the work of Yang Mills and Hideki Yukawa?
um, I would say there is overlap between. I mean, they some. Okay, so Yang Mills theory, and remember this is two people, right? Robert Mills and I keep forgetting his name, Yang. Uh, so they were studying forces and pure forces at that. The work of Yukawa has more to do with nuclear decay and the aftermath of um, trying to understand the. I mean, they were understanding behavior of the nuclear decay forces and kind of tackling it from a more pragmatic point of view. Because if people were familiar with, let's say, the so-called Yukawa potential, it's a model. It's a simplified model to study how radioactive decay works, right? And it turns out that when you have a Yang-Mills theory, that's like the electroweak theory, and you have the Higgs field, and when they're arranged in a particular way, I don't want to go into details, you will end up with something like the Yukawa theory. Um, so these Yang-Mills theory had the power to kind of behave very differently depending on how the particles configure. I think we talked about a little bit of that in one of our really old episodes, like the phases of forces. If you're interested, you can try to check that out. Maybe you'll find more information there.
Yeah. So I realize we're basically at time, and so I wanted to give you a chance in our tradition of any words of wisdom that Yang and or Mills or even Yang Mills has taught you.
Yeah, I mean, I know that this is, of course, the Millennium Prize problems are not the only interesting problems in the world to solve, right? Like, it's a somewhat sensationalized, but at least it's highlighting the fact that um, it's highlighting the fact that physics is still generating very interesting mathematical questions for the mathematics community to solve. And there's always been this great collaboration between math and physics, and this is a great exemplar of that. Um, and I think, in my mind, it probably reinforced the idea that our universe is mathematical, and that's kind of interesting. And I think in recent years, the more collaborative math and physics becomes, we only get more insight. And you can also look at the single one Millennium Prize problem that was solved, the Poincaré conjecture. It was well known that one of the tools they used to prove the theory was what we call renormalization,
Hmm.
and that framework was used in particle physics, was developed in particle physics, and initially it was not well defined. We didn't, it was kind of just hobbled together to make something work. But later on, people really took flight with that idea. I mean, I don't want to give physics all the credit, but like seriously, renormalization is an idea born from physics, and I would not be surprised if maybe even some of the other um, Millennium Prize problem, maybe the solution will have inspirations from physics, because I think in my mind, I'm always of the opinion that nature is smarter than any physicist in the past or alive, right? So I think, and I always have the strong opinion that physics is really truly discovered. We don't invent physics. So hopefully, nature will continue to surprise us.
I'm totally willing to support you if you want to give all the credit to physics. I'll make that statement that you don't have to. So if people don't
All
like
right.
it, they can blame me. Yeah. Wait. Oh, I guess another question came in. I'm having trouble reading this. Let's see. Poincare conjecture was convergence of random walk in multiple dimensions, right? I assume that's a question. I don't know if that's a question.
I'm not sure. I'm not sure that's correct. At least from my understanding, Poincare conjecture. It was a little bit of detour. I mean, our Corcas discussion is probably formally over, but Poincare conjecture has to do with the fact that if a space it has to do with something called simply connectedness. If you draw a circle, can that circle shrink to a point, right?
Hmm.
And the conjecture is that if you have a space, an object that every loop can shrink to a point, then it's basically a sphere. You can mold it like a Play-Doh and turn it into a sphere, right? And I think
Hmm.
the only dimension that was missing was 3 dimension. That was very difficult. Um,
Hmm.
so it was proof in other dimensions, but three was the trickiest part. And the way to prove it was they found a way, to deform any arbitrary objects into a sphere. And once you do that, that's kind of like a constructive proof, sort of, at least in the mathematical way. And the way they were able to mold that object through, they basically to smooth it out. Let's say you have some object that's heinous looking, like with some crazy sculpture, some abstract artist was making, right? And you want to deform it back to a sphere. Yeah. The idea is they use renormalization flow, and some of the audience was saying the Ricci flow, um, which was used in particle physics. You look at the behavior of a system as you zoom out, and it's somewhat similar. You kind of smooth it out. When you zoom out, features get smoothed out. And using these ideas, I forgot the mathematician's name, probably many mathematicians, they were able to bypass the singularity and finally to mold any object in 3 dimensions, smooth it out into a sphere. And then the conjecture was proved. So something along the lines. I don't know the details, not a mathematician, but
Hmm.
but a very physics-esque result, I would say.
Yeah, it is interesting to see how much physics comes in. Yes, to answer our audience question, it was solved by a Russian mathematician who denied the prize, even though I believe he was living on his mother's pension. Yeah, it's an interesting history for those who are interested to check it out. So yeah, so on that note, I want to thank everybody for joining us, and we'll see you all next week.